Hello students, your physics teacher Hassan Darwish with you. In this video, I'm going to explain Lenz's law, and as you see, it's related to the direction of the induced current. Now, Lenz's law states that a variation in the magnetic flux produces an induced current in a closed circuit, right? We verified this in the previous experiments through previous videos. Now, the direction of this current is in such a manner to produce effect opposing this variation. Means what? Means the induced current is created to oppose the variation or the sense of variation of the magnetic flux. Simply speaking. Let's see how. Remember experiment 1? When we approach the bar magnet into a coil, the galvanometer detects the passage of an electric current. Let's find the direction of this induced current by applying Lenz's law. So here determine the direction of the induced current in the circuit when the magnet is either approached the coil or moved away from it. So let's consider case 1 first. Magnet, bar magnet here, approaching the coil. Okay? First point. What happened to the flux through the coil if you approach the bar magnet? Magnetic flux phi increases, right? The flux inside the coil increases. Okay? Step 2. By Lenz's law, I induced, let me write it like this, I induced is produced or created to oppose this variation, I mean to oppose the increase of flux. It's produced to oppose this increase. This increase of flux. How? How is this? By producing effect, right? So, to produce effects opposing this variation. Now here, the unpole of the bar magnet is approaching the coil. Now you want to oppose this approach of the magnet. What do? An unpole, write them in black, right? This face of the coil act as unpole to repel this unpole of the bar magnet, and this face act as S-pole. Why is this? You know that an electric current in a wire creates magnetic field. Is that true? Now, since this current in the coil is an induced current, I will call the magnetic field that is created inside this coil an induced magnetic field. And also you know that inside a bar magnet or inside a coil or a solenoid, the magnetic field is always from the S-pole into the unpole, right? So this is B induced. This is the induced magnetic field created by the induced current. So you know the sense of the magnetic field, induced magnetic field. You need to know the sense of the induced current. How? Step 3, applying the right hand rule. Applying the right hand rule. Clear? In the same way you applied it to find the positive sense of the coil. Now, look at B. This is a thumb. Okay? Here, this is your thumb. This is a thumb, which points in the sense of B. Now here are the four fingers of your right hand. Okay? Here is your right hand. You see? Now this is the sense of the current. Here, this is I induced, or the sense of the current. So the sense of the induced current is like this. Okay? Some people call it anticlockwise if you view it from this point. So to find the sense of the induced current, I have applied 3 steps. Step 1, look at the sense of the variation of flux. Step 2, applying Lenz's law, which states that the induced current opposes the variation of flux. Step 3, applying Lenz's law. Okay? Now let's go to the case where the coil is moved, where the magnet is moved away from the coil. Okay? So here, case 2, bar magnet moves away from the coil. Step 1, what happened to the variation, what happened to the magnetic flux linking the coil? You know that. Phi decreases. That's step 1. Step 2, applying Lenz's law. Lenz's law. I induced is created or produced to oppose this decrease of flux. Decrease of flux. Now, how does it do it? How? I always ask how it opposes the decrease. Now, the magnet is moving away. So the induced current create effect in the coil to oppose this movement away from it. So this phase, use also the black color, act as S-pole. Clear? And this phase act as N-pole. Why is this? Why do we have S and N? Because there is an electric current in the coil. And according to Ørsted experiments, electric current create magnetic field. But this current is induced. So the magnetic field, I call it induced magnetic field, which is always inside the coil from S pole to the N pole. So this is B induced. Okay? Now step 3, by right hand rule. You want to find the direction. Right hand rule, as I said, and as I told you before. Always use 3 steps. Now, according to the right hand rule, okay, our thumb is in this way. It has the same sense as B. So here's our thumb, okay, of the right hand. And here, our right hand. So this is the palm, okay? This is the palm. So what is the sense if you turn the palm, if you turn them down like this? So this is the sense of the induced current. It's very easy. Okay, any problem? Now another application, Laplace's rails. Laplace's rail consists of the 2 rails here. Okay, this is rail 1 and this is rail 2. And we have here a copper wire which may slide on the 2 rails. Here we have connected the galvanometer. Here it is. Okay? So where is the closed area? Look at B. B is always from the N pole to the S pole, means downward. So here it is. This is B. Here is the closed circuit. Be careful. This is the closed circuit or closed loop. Okay? Now we move this wire by applying on it, say, a force F. Here it is. We want to find the sense of the induced current. Step 1, we look at the sense of variation of the flux. Step 1, look at sense of variation of magnetic flux. How it varies? We know that phi is equal NBS cosine theta, right? So n, which is the number of loops, is 1. And B is constant. Why constant? Because we have uniform magnetic field between the poles of a U-shaped magnet, right? So B is uniform, means B is constant, times the area of the loop. Here is the area of the loop, times cosine theta, the angle theta between the positive plane and B, which is also constant, which could be 0. Suppose it is 0. So times cosine 0 is 1. So we get BS. B is constant, and S here, as the rod moves, variable. In this case, the area of this loop is decreasing, right? So since S decreases, flux decreases. So now we know the sense of variation of the magnetic flux. Step 2, we apply Lenz's law. Lenz's law. You know that induced current always opposes the variation of the magnetic flux. So I induced opposes the decrease of flux. Right? How? We ask how it opposes it. In reality, here there are more than one way to explain how, but I will follow the simplest one, because here we have a loop and we know that the external magnetic field, which is blue in this case, I draw it B, due to the bar magnet. Okay? So you know that an electric current in a wire creates magnetic field. Is that true? And the electric current here is induced current. So we have to create induced magnetic field. Let me draw it using red color. But you want to oppose the decrease of flux, right? So the flux increases. Then B induced has the same sense as B to oppose the decrease, right? Because if B induced is opposite to B, then you are, for example, trying to decrease the flux, but we want to oppose the decrease of the flux. Clear? So you know B, I. Now, third point, applying right-hand rule. We use the right-hand rule. You know now the sense of B. You want to know the current. How? This is the thumb. B, thumb is downward. This is the thumb. Okay? Here is your thumb. Now, you try to turn your finger in this way, the other fingers in this way, right? To have your thumb down. So the sense of the induced current must be in this way. Clear? So third point, write it here. Point 3, applying right-hand rule. Thumb has the same sense as B induced in this case. So I induced flows or passes as shown in the figure. Now you can apply Lenz's law in any electric circuit if you follow the following 3 steps. It's very easy. First, find the sense of variation of flux, then find B induced, then apply the right-hand rule. Okay?